All right, let's jump right in. We're going to trace the incredible 80-year quest to build a thinking machine. It's a journey that started with this one super simple idea, and now, well, it powers some of the most advanced tech on the entire planet. So you gotta wonder, right? How does the AI we use every day actually think? I mean, we see it creating stunning art, writing code, having conversations that feel real. But to really get a grip on how it all works, we have to rewind the clock. We've got to go way back to the beginning, to this single idea that's been cooking for decades. And you know what? It all kicked off with an idea that's almost poetic. It was inspired by the most powerful computer we know of, the human brain. The whole quest was basically, hey, can we build an artificial version of the brain's most basic part, the neuron?
Okay, so our story begins way back in the 1940s. I mean, this is long before the silicon chip even existed. It all started with this really fundamental question. Could the process of human thought actually be described with math?
So these early years had this really wild up and down arc. First, in 1943, we get the theory, basically a mathematical blueprint for a neuron. Then, fast forward to 1958, and this theory becomes real with something called the perceptron. This was a machine that could actually learn to see patterns, and people got so excited. But then, bam, just over a decade later, in 1969, a book, literally called Perceptrons, comes out and brings all that excitement to a screeching halt. It basically pointed out a huge, fundamental flaw. So what was this big, fatal flaw? Well, the perceptron was, at its heart, a pretty simple decision maker. It could learn to separate things into two piles, but only if you could draw a single, straight line between them. Think about it like this: sorting apples from oranges by color. Super easy for a perceptron. But what if you wanted to sort them by, I don't know, a combination of taste and texture at the same time? Nope, the perceptron just couldn't handle that kind of complexity. And that right there was the problem. The real world isn't neat and tidy. It's messy, it's complex, it's what we call nonlinear. And because the perceptron couldn't deal with these more complicated problems, the whole field just hit a wall. A period of serious disillusionment started to set in. And this period became known as the AI winter. It was brutal. Funding just dried up. Research slowed to a crawl. That initial incredible promise of a thinking machine, it suddenly looked like a false start. The entire field was stuck, wrestling with one single massive problem. And the crucial question was this: how could a network actually learn from its mistakes? You see, the simple, single-layer perceptron had no good way to figure out complex errors. And if you tried to stack more layers of these neurons to make a deeper, smarter network, well, there was no way to train it. How could you possibly tell those neurons buried in the middle what they should have done differently? Answering that question, that was the key to everything. The answer, the huge breakthrough, was an algorithm called backpropagation. And it's this really elegant idea. Basically, the network makes a guess, checks how wrong it was, and then sends that error signal backward through all the layers. It tells each connection exactly how much it messed up and how it needs to adjust itself. This one algorithm unlocked the potential of deep, multi-layered networks. I mean, it is so fundamental that it's still at the heart of pretty much every major AI system we use today. A total game changer. So, with the ability to learn now finally unlocked, the field just exploded with new ideas. It was like a dam breaking. Researchers started designing all these specialized networks inspired by different parts of the brain to solve very specific kinds of problems. And this led to two really powerful new architectures. So on one hand, you had convolutional neural networks, or CNNs. These were inspired by our own visual cortex, and as you can guess, they turned out to be brilliant at understanding images. On the other hand, you had recurrent neural networks, or RNNs. These were built for sequences, like text or speech, using these feedback loops to kind of remember what came before. And a huge innovation here was something called an LSTM, which basically gave these networks a reliable long-term memory. Okay, so now we've got the learning algorithm, backpropagation, and we've got these cool specialized architectures. But they hit another wall, a big one. These networks, especially the CNNs for vision, were just computationally starving. They were so slow. Training them on the computers back then took an impossibly long time. The ideas were literally decades ahead of the hardware. And then everything changed. It wasn't just one thing. It was 3 different technologies which had been developing separately that finally came together at the perfect moment. And when they did, they ignited the revolution that we're still living through right now. The year was 2012. You can think of this single year as the clear dividing line. It's the moment that separates the theoretical era of AI from the practical, modern AI that we see all around us. So, what happened in 2012? At the big annual ImageNet competition, a deep convolutional neural network called AlexNet didn't just win, it absolutely shattered the records. It destroyed the competition. Its performance was so far beyond anything anyone had ever seen that the entire research community just stopped and took notice. The AI winter was officially, definitively over.
So what made this all possible? What was the magic recipe? Well, it was 3 key ingredients coming together. First, you had those sophisticated, deep CNN architectures we just talked about. Second, you had massive internet-scale datasets like ImageNet to actually train them on. And third, the final, crucial piece of the puzzle was the raw power of GPUs, or graphics processing units. These chips were originally made for video games, but it turns out they were absolutely perfect for the kind of math that neural networks need to run.
Okay, so the deep learning revolution gave machines superhuman vision, which is incredible. But language was still a huge challenge. And this leads us to the most recent, and you could argue the most impactful chapter in our whole story. You see, a new problem started to become really obvious. How can these models understand the relationships between words in very long sentences or paragraphs? RNNs were clever, but they had this fundamental bottleneck. They had to process sentences one word at a time, in sequence. And that made it really hard for them to keep track of the whole web of context. The meaning of a word at the beginning of a paragraph could be totally lost by the time the model got to the end. Then, in 2017, a landmark paper was published with this incredibly bold title, Attention is All You Need. And it wasn't just a clever name. It proposed a completely new architecture that would solve that context problem and really change the entire course of AI forever. It was called the Transformer. The Transformer's genius was really threefold. First, it completely ditched that one word at a time approach. It looked at the entire sentence all at once. Second, it introduced this powerful mechanism called self-attention. This let the model figure out the importance of every single word in relation to every other word, capturing context like never before. And finally, its design was just perfect for running on GPUs, which meant you could scale these models up to the massive sizes we see today in things like GPT-4. So, when you look back from a simple on-off switch to a model capable of complex reasoning, the story of AI hasn't been about one single eureka moment. It's been more like climbing a ladder of brilliant solutions to what seemed at the time like impossible problems. I mean, think about it. We've gone from the simple perceptron that could barely tell 2 different shapes apart to models that are starting to show signs of actual reasoning. It has been an absolutely incredible 80-year journey, and it leaves us all with the biggest question there is. What's the next impossible problem that AI will solve? What wall will it hit next? And what brilliant new idea will help us climb over it? Thanks for watching.